Thank you. So I was really honored that by your kind invitation to join the summer school. And today, I'm very pleased to introduce for you what we are really doing inside the Department of Software Science in Caltech, and especially within the data science group. So the idea to introduce what is data-driven. So the idea that we are collecting data, and this data is collected to extract knowledge, and this knowledge is meant to support decision-making. So this is I would say, the landmarks of all what we will explain and show later. So what is urban mobility? So mainly the focus of urban mobility would be this traffic congestion. So the challenge, how we can reduce the adverse impact of traffic congestion in terms of CO2 emission, in terms of fuel consumption, which is the economic part, in terms of impact on mental and physical health of the drivers. So that's why even we try to lower the duration of the trips. So for today, I would suggest for you this outline. So at first, I will start by providing kind of mouth-watering introduction and motivation, especially in terms of numbers that would matter, to show what are the losses, what are the assets that we are really missing through this congestion. Later, I will show you two use cases that we are developing. The first one is about travel time estimation. And the second one is the smart traffic light management. Okay? So this is what the initial plan. Then, in the meantime, I was working on one Ride in Europe proposal, which is meant to be road safety. So this road safety, it is meant where we are discussing about what we call this V2X. It means that the vehicle are communicating with vehicles, and vehicles are communicating with the infrastructure. And then we will see that later vehicle will communicate with the other types of entity that can be drones, or can be scooters, or can be e-bicycles. So this is how we can manage the road safety within these new settings. But up to what is the connection between, for example, traffic light and road safety? You know, I would like that you help me to find this red thread between traffic light management and road safety.
Green passage.
The idea is very simple. The road safety, if you are better managing the traffic light, it means that the drivers and cars are spending less time on the road. Then we are improving the road safety. This is one aspect. The second aspect, there is a connection between the fact, if you are better managing the traffic light, you are improving the air quality since you are reducing the CO2 emission. And there is a connection, as in studies they are putting on the table, the connection between the air quality and the number of car accidents. So with this road safety, what we are starting developing, I will present the architecture, and the goal of today is I'm seeking for feedback from your side. So I would like that you criticize the architecture that I would like to propose to introduce today. So in this architecture, the traffic light management is seen as one of the services of the framework, which is make things really very original. So now, please feel free to interrupt me at any time and to ask all of the question, and I would like to make this kind of talk very, very interactive, okay? So in the current reports, they are indicate that the global population would reach in 2023 8 billion. So, and most of this population, they are working and living in cities. So there is the fact that you need to commute from your residence to work, and then you need to take your car. So this commuting activity is obliging you to put it in more traffic, so it's in there. And the congestion is coming from the fact that citizens are finding the commuting activity very, very tricky. So that's why they need to take their cars. It's important to highlight that the fact that traffic congestion wasn't still the primary concern of travelers, and it is bringing this adverse impact on the mental and physical health of. So these are numbers that are very talkative. For example, due to this congestion, we have 135 million deaths for traffic accidents per year. If you take, for example, 7.7 billion hours for travel delays with the numbers from 2021, this traffic congestion is costing 166 billion euros for the Euro economy with respect to statistics in 2019. And this pollution, 4 million deaths from outdoor air pollution with respect to data from 2016. So I think that these statistics are the clear evidence there is some urgent action to be undertaken. Let's put the focus on this statistic. For example, what is the percentage of extra time due to congestion in 2019? Unfortunately, for example, if you see Poland is the only European country who's reached to put 3 cities among the top 10. This 59% in Moscow or in Istanbul, for example, it shows that a driver from the same journey or same trip would spend more 59% extra time. 59% extra time while you are driving. It means that 59% more time, more CO2 emission, more stress, more fuel consumption. So this is, and the second one is the most traffic jam prone cities in Europe. So we find Lodz, Bucharest, Moscow, and so on. So this is their statistics that they are giving evidence that that we need this action to undertake. So in terms of fuel consumption, or in terms of congestion, sorry, there's something which is, unfortunately, there is overlooked. The fact that this urban noise, many people, they are putting on the table the fact that there is fuel consumption, CO2 emission, air quality, but unfortunately, they are disdaining the fact that one side effect of the congestion in the urban noise. And the urban noise, for example, this World Health Organization reports that exposure to loud noise causes high blood pressure, hearing loss, heart disease, sleep disturbance, and stress. So that means that we have not to disdain what the adverse impact of the urban noise. So what is the issue, the solution? There is two pathways, I would say. The first one would be to change the infrastructure and to go through what we call this mass mobility as a service. Mobility as a service means that we would like to encourage citizens to rely on car sharing, on bike sharing, or scooter sharing, and to not take their cars, or even to ditch their cars, and to rely on the public transport. So the question is the following: regardless of the cost that which is the first set from being affordable, do you think, for example, in the northern countries like our country, in Estonia, in the rude weather condition in winter, we can rely on to take my kids to school, and then from the school I need to take the car sharing to the university where I would work. Do you think that is feasible? I think that it's not that feasible thing, and in addition, that is very costly, and it takes time to be implemented. And for example, I think that Estonia, in northern countries, it would take a lot of time to change the mindset where really people are really convinced by the need to ditch their car and to rely more and more on the public transport. On the same time, the public transport authorities need to take the effort to be all ears for the needs of the citizens and to adapt the offer of public transport. So this is one pathway. The second pathway is to say, would it be possible that we leverage the existing infrastructure? The existing infrastructure is we have already traffic lights, for example. Would it be possible to optimize these traffic lights? And then we would see what would be the impact. So the idea that I messed it up as usual. So I would say the idea is to say that an improved traffic light system will lead to better traffic management and therefore more peaceful urban area, since we're expecting that by doing so, we are reducing the urban noise. So the main objective of the traffic light management is to reduce, optimize the cycle timing at intersections to significantly reduce the congestion and improving the environmental quality, especially the noise pollution. But is it the traffic light, this optimization of cycle timing, do you think that is the magic one that will remove congestion? Up to you, is it this magical one that is it sufficient to manage, to optimize the cycle timing to remove? Our objective, we need to remove once for all. In my humble opinion, I think the answer is no. What we are really doing, we are trying to process data, which is the visible part of the iceberg. We need to go through and to analyze what we call this journey to work. It means that we have a lot of theoretical work that needs to be undertaken in order to analyze what kind of insights that can be leveraged from building a graph, where in the nodes we will see what are the patterns, the numbers of patterns from people that are commuting from work, from where they are living to work. So that's why what they call it, the analysis call it journey to work. And then with different KPIs coming from the graph theory, they are able to provide you insights. For example, what is the maximum, the meaning of maximum click or betweenness from, which are KPIs from complex graphs that give you the hints how to expand the urban planning in order to reduce the traffic congestion. So this is the idea that we are developing, is to can only be complementary to something which should be done in depth to understand what are the commuting patterns. So what are our requirements? The requirements, they are very simple. We would like to have develop this framework that will provide what we call this immediate deployability. It means that we would like to provide a solution that next week it will be implemented in Tartu or in Viljandi or in Tallinn. It means it should leverage the existing infrastructure. Why? Actually, most of the carried out tests or the approach, they are supposing that we are 15 or 20 years ahead, and where cars are able to communicate between each other. And cars also, or vehicles, are able to communicate with the infrastructure. The second requirement is data-driven. Data-driven means that we should be able to collect data, but the collection of data should not be a goal per se. We would like to collect high-quality data. So that's why we will see that later we'll do multimodal data fusion to increase the data quality. And once we increase the data quality, we are sure to have very nice prediction, accurate prediction that would ground the decision-making process. The third requirement, it should be near real time. Near real time means the zero delay feature would like to provide the proactivity feature. It means that we would like to not base or ground our decision-making process on immediate data. So that's why we rely on prediction. Why prediction? We would like to give hints to the decision makers that, for example, that soon we will have spikes of congestion and you need to undertake the right action. It's up to you to adapt the strategy of traffic lights. The fourth one would be extensible and combinable set of sources. We would like to leverage all the sources of data that are available. Can be, for example, sensor data, like speed, urban noise, CO, traffic light, traffic data, radars, lidars, videos, satellite images, and so on. The second and the penultimate requirement is the scalability. If you keep in mind that we would like to be able to manage these millions of connected CAV, it stands for connected and autonomous vehicles, thousands of intersections, should be able to do it. And then the resilience. It was last but not least the resilience to cyber attacks. The goal of that is to keep in mind whatever would be the impact, the strength, the reliability of your system or framework that you would like to put at work, if you are not having this seamless shield to protect you against the cyber attacks, all the efforts that we have done are really pointless. So the resilience, it's the capability to provide seamless shield to the cyber attacks is very important thing. So we in our group we developed this urban mobility information hub, and I have chosen to provide for you two use cases. First one is travel time estimation, and the second one which is about the traffic light management. And then we also developed for recommendation of charging spots. So the recommendation of charging spots is also illustrating, and it's I will connect it later to the infrastructure. The recommendation of charging spots is the illustration of what we call data collection, knowledge extraction that would ground for decision. So what we have done in this recommendation of charging spots, we are the first group to develop a very nice tool that would, if you're providing a point A and point B, which is destination, would provide for you the shortest route. But given that is taken into consideration your need to charge your electric vehicle. So it is not based on raw data, but it is based on prediction. It means that we are collecting data, the raw data about the availability of the charging spot. We are combining it with other type of data to provide you or to recommend for you where to charge, where to charge, where the charging spot will be available as soon as you reach the charging spot. Since you have to keep in mind that the charging of trucks or electric vehicles takes time, at least 20-25 minutes. So this is something that we also developed. So so let me please quickly introduce for you. It is on purpose that I try to not dig into the technical details. I would like just to provide you the general idea to put on the table what are the contributions. So why travel time estimation is so important? So travel time estimation, would you imagine that Bolt is not using the right travel time estimation? The business model of Bolt, the car sharing this mobility as a service of Bolt, would collapse Bolt if they are not providing the right estimation. So then if they are not providing the right estimation, they are not able to provide the right charging to the client. First. Second, for example, why we need this travel time estimation for our charging spot recommendation? If you are not able to correctly and precisely and sharply estimate the arrival time to the charging spot, it means that all the interest of our recommendation will collapse. Since you will arrive, we will tell you that go to this charging spot, and in the meantime, we mess with the estimation of travel time, then you arrive to the charging spot and you find that it's not available. It's already taken. So that's why the travel time estimation is the ground for many other applications. And that's why I took the liberty to and choose to present it for you. So travel time estimation, though, that we developed a couple of years ago, a new approach, which is, the idea is to split the data, this time series data, into what we call this meaningful zones. By doing so, we are able to overcome the path and what we call subpath spatial mismatching problem. In addition to that, we make use of temporal and some external features, for example, hour of day, weekday, and so on, to accurately learn correlation and dependency of complex patterns among data types. So our approach was split in two steps: data pre-processing and model training.
Sorry to interrupt. A small question.
Yes.
Thank you first for the nice introduction with respect to the travel time. So I'm curious about those zones. How did you define them?
What do you mean?
In the previous slides.
Yes.
Meaningful zones.
Yes, meaning we are split them according to the location.
So only the location. There is no other characteristic.
No, no.
Okay.
We were using two data sets from the state of the art, and we are showing that we are able to locate these meaningful zones, which was the strength of our proposal. So we were inputting this origin destination matrix, and then we are also adding these input features, which are the embedding features, hours of the day, taxi ID. So the data was the taxi data set. And other continuous binary features, speed, is a weekday, and so on. So all of this data is input to the computing layer, and then we are concatenating this ILI where you enter, finding the regression for the model training. So as I said, we use two commonly used data sets from during the community, the Tartu and Chengdu in China. We are not able to get the interest of Bolt to ensure data for Bolt, unfortunately. So, and use the evaluation metrics. So what you notice in terms of our MCE, that our project is providing the list of the error for both data sets. In terms of MIE, the same. And the same of MAP. So we have, for Tartu, we were beaten by this approach. But for Chengdu, we are the best. So I can say that we have very competitive, very interesting travel time estimation algorithm that can be leveraged by the industry. So let's move to the second use case. Yes.
So these results look really amazing. The differences are not small. I mean, proportionally, I mean, relatively, it's like several-fold difference. Could you please show the diagram again, the previous? Yes. I mean, it's almost like 10-fold difference and more with other methods. What's kind of the key reason behind that?
I can share the paper with you. But the fact that we are embedding this extra information, that's why I call you that we are adding, we're starting point at this origin destination metrics. But in addition to that, we are taking into consideration some extra. We are taking what we call this ecosystem. So that's why we're able to improve the quality.
And the comparison is against the ground truth of actual travel times?
Yes, yes. So that's why. So this is this is the ground. This data layer were used at Porto and Chengdu, the one that were used by all the approaches that we were compared to, and they, when I told you that they are the best of the best. And this work was published in A conference, Blanket A. So it means that we know whom our competitors.
And so the scale, if you go again to the diagram, the next, so the scale, the y-axis was seconds, right? So, okay.
Yes.
RMSE in seconds, and so, for example, on the right-hand side, yeah, so there is, okay, but 10 seconds is average. Okay,
Yes,
and here
we had
yes.
stunning results, and you will see also the other use case. You will see we are outscaling all the other competitors.
Because I'm just trying to think of how much noise there is in traffic. I mean, some things you just can't predict because you don't know whether at that point a human starts to cross the street or not, and that will make a difference of whether the car needs to stop at that unregulated crossing
Yes,
or not.
I completely agree with you. That's why we were not that happy with this performance. That's why we wanted to have some real live data set. I would say, that's why we were even trying to convince Bolt to share with us data. Bolt asked me to give the paper, and that's it. So the use case, yes. So the second contribution is about this traffic light, traffic signal control, and it was the paper was accepted, July 2023. In this paper, in this publication, we have done extensive experiments in Tallinn, as I will show later, in one of the most congested traffic lights intersection, which is Tampsaare-Sopuza. So the goal is to, I would say, what would be your, the dashboard that you have dreamed of? May I ask you a silly question? If you see this dashboard that you have at the main entrance, what is your interest?
See how energy efficient it is?
No, are you seeing your contribution? It means that, are you seeing that what you are providing or the effort that you are doing are meaningful to reduce? For example, do you know how much this system, how much do you have your earning in terms of reduction of energy? So that's why when I'm about to try to convince the Department of Transport in Tallinn or in Tartu, what would be the dashboard that you are dreaming of? So I would say, in this, I would like to see that the impact. We are reducing the urban noise in our city by 4.54%. We're reducing by the 1.51%. This is what we are showing, that what we are doing, what is the impact of our actions. And then we are also decreasing the average waiting time per car by 2 minutes, and then the 3.1 CO2 emission. This is what we would like to. We would like also to provide to the Department of Transport, who is managing, that this is what we call this prediction. The idea that we would like to provide you the information that on time. What's the point if I tell you now there is a congestion? It's too late. So what I would like to say that now it's currently we are here, but soon you will have this spike, and then we would like that you need to undertake if you would like, you are not trusting us, please then take the right decision and adapt your strategy to lower. Then in this dashboard, we are providing also this performance prediction. So the idea what we would like to provide a kind of what we call this digital twin. Digital twin, what would be the impact of changing the strategy of traffic light? For example, here, if you choose your key performance prediction by CO2, for example, per car, you will see here, if you stay idle, this is where you are. This is your level. You are not doing nothing. But if you adapt your strategy, if you choose, for example, the green one, this is your levels, you will see that how much you will decrease the CO2 emission. It means that we are not telling you that we are decreasing, but we are also giving you claims how much you are decreasing. So it means that this dashboard would provide you the information for you as decision maker, and also for the citizen Lambda that he's seeing, oh, the city, the mayor and the city, they are doing very hard work for that. Okay. So this is the dashboard that we are dreaming of to provide for any intersection. For example, I say here it's green, but here is the stroke that you need to manage. Okay. So what are usually the strategies for traffic lights? There are two types of strategy, what we call this fixed time and this traffic responsive strategy. Okay? For traffic responsive strategy, we check it the rated work. And then for the traffic, for the response strategy, you will find much wealthy number of rated work. Okay, many of them they are using the reinforcement learning. Okay. So with our Ecolite Plus, Ecolite Plus is coming after Ecolite. It means that we improved our Ecolite, and Ecolite was tested on data that we collect from Helsinki city. But Ecolite Plus was tested on real-life data that we collected in the city of Tallinn. So the idea that two main features, the sustainability, so we would like to incorporate noise as an environment input feature, and the second one is the proactivity. The idea to provide these insights on time in order to the decision maker will undertake the right decision. So, as I said, we are collecting data from the environment, okay? And then from this data, we are doing this very advanced data fusion, okay? So we are including the phase number of vehicles, every waiting time, queue length, noise. And all of this data is able to provide what the future noise prediction evaluation. Then This feature noise, they are driving the model to adapt the traffic light. And we are using this deep reinforcement learning, and so the model is driven by rewards. So we compared our performance in terms of noise predictions. So we showed that we are better than ARIMA, but the purpose was not to compare the noise prediction. The purpose was to compare this traffic light performance. So let us focus on the data. So we were using this multimodal data. So we were using noise sensors, video cameras, weather data, and TomTom traffic data. And so we considered almost 2 months from 15th of February until 6th of April. And the frequency is 1 minute frequency data, okay? So, and we are considering Tampere-Sopuruza intersection in the city of Tallinn. So if you concern the green one, it's the second one, the blue one is the noise. The third one, it's about fuel consumption, and what this one should be, CO2 emission. So in terms of CO2 emission, what we are showing that this was Ecolite. And then is what the previous version Ecolite was what was tested in Helsinki. So what we see that Ecolite Plus is reducing, it's outperforming all the other ones, the competitors, in terms of CO2 emission. In terms of fuel consumption, as you may see, we are largely outperforming all the other ones. And in terms of noise, we also please do not say that the results are so true that they are not believing them. Please.
Was included in the TomTom traffic data? In the trajectory, or how long?
Yes.
And how was the fraction of drivers with respect to?
So actually, we had agreement with TomTom. TomTom, we were using TomTom since we were not able to fully use the sensors that we have in the city of Tallinn. So that's why we are using TomTom. And unfortunately, many of the sensors, they are not working, which is, expectable. But it shows that the data that we're collecting from the sensors were the main hurdle towards better performances. For example, if we are collecting 10,000 rows, we have 7,000 with missing data.
We are very
I know.
familiar with
I know. So that's why we were using this TomTom data to complete first. So, and then we are also using the cameras. So the idea, the purpose of this data fusion step, which is very important, is not only to rely on urban noise sensors. Is to rely on, we are duplicating the sources of information in order to mitigate the impact of missing data. So we are able to, that's why we say this multimodal data, we are able to integrate multimodal data. Images from the cameras of the city of Tallinn. So that's why we are able to reduce. So thanks to this deep reinforcement learning, so deep reinforcement learning, the algorithm, the traffic light is driven by the prediction. So that's why I say the prediction, the quality of the prediction, they are in strong connection with the quality of the data that you are collecting. That's why we try to spend a lot of time and energy to collect reliable data from these multiple sources that we are fed to the algorithm for doing the prediction, and then you are able to reduce the traffic data. Do you have any estimation how much we are earning in terms of fuel consumption? Money. So this is the impact. So in that time, I think in April, we were the fuel price was $1.90. So each hour we were able to save $1,689, which means that per year we are able to save 14,700,000. So these huge numbers, you need to take in consideration that the fact that they are simulation. But when you need to go to the field, this is another point of view. When you go to the field, you need to ensure that you do not have internet. You need to ensure that all the data that needs your algorithm for doing the prediction, for the collection, for data fusion, for the prediction of the urban noise, and the implementation of the traffic light, they need to be implemented on the edge. And there is a lot of, I would say, gap that you need to mine between the performance that you would obtain on the cloud when you are no limit for your resources, and how you bring the strength of this AI model that would develop, how you would bring them to the edge. So this is something that we are working on. We are working in this summer. Okay. So the conclusion that we saw, we are very happy to have this Ecolite Plus. So this is the second part, which is about our perspective. That's we are trying to think. This safety road in V2X vehicle to everything settings, and we are invited to take part of this proposal with Horizon Europe. What is this Vision Zero when it comes to the road safety? So the Vision Zero would like to, by 2050, there is our goal, 0 deaths on the road. So I just beg your patience to just, I will explain the connection between what we are explaining, travel time estimation, this traffic light management, and how it is connected to road safety. The idea is coming from the fact we started developing the idea. Now we have secured this Ecolite Plus. Ecolite Plus is based on the fact that we have cameras, we have sensors, what we call this infrastructure, and we are collecting the data, and then we are processing the data for taking a decision. But in V2X settings, in 15, 20 years ahead, vehicles will be able to communicate with vehicles. Vehicles will be able to communicate with infrastructure. What does that mean? It means that the cameras that we have at the level in the traffic light is pointless. The sensors that we have in the traffic lights, urban noise, CO, or the air quality sensors that we have used to have them now they will be pointless. Why? The reason is very simple. Actually, from now on, it will be cars that will do the trick. Cars will have their own sensors, and then they collect data, and they have to share it. With whom? How? This is another issue. Then, from now on, our traffic light will be blind. He has no any more cameras. Do you know why? Actually, he will be able to sense the congestion status by only since he will by log. Since each car, each vehicle approaching the traffic light, or what we call this roadside units, he has to, to decline its identity. So that's why he will know by this exchange how many cars is in front, and he will able to detect the congestion status. So he has we do not need anymore this camera, and then to be able to count how many cars they are in front of the traffic light. So in these settings, so we wanted to develop EcoLight++, where it is adapted to V2X. We wanted to know what things would change. Then we were contacted by these guys of the proposal, and we were asked to join, but in terms of road safety. The road safety, I will prepare some KPIs. As you will see in the V2X settings, things will change. Now we have, the European Union is setting 8 KPIs. But later, you will have to add new KPIs. For example, are you able to detect one of the KPIs is in condition to drive? Are you drowsy? Are you tired? Are you drunk? Are you in condition to drive? This is a new KPI that we would like to introduce. Are you drunk? So to be drunk, how this one, let me quickly, yes. These are the KPIs. For example, this is the 8 KPIs: KPI speeding, KPI alcohol, KPI vehicle safety, KPI infrastructure, KPI post-crash care. It's the time elapsed between the emergency call, the collision, and the arrival of the scene of the collision of the emergency services. These are the KPIs. So the idea of this proposal is to improve the verification means, as well as introducing new KPIs. For example, this CO2 emission, urban noise, fuel consumption KPIs. Actually, all the current approach of the European Union, they are not able to assess it. For example, the KPI alcohol, how it is measured? What we call this field sobriety, that's the FST. They are, these random controls. So the question is, do you think that these field sobriety tests are enough in the context of this SMAS, mobility as a service? No. Now I take Bolt. Bolt is offering this service to be able to rent on the go. It's true that you have a driving license which is registered, but is Bolt aware that the fact that this guy is not in condition to drive? Then the idea, we would like to have a verification mean. So it means that what would be the impact on the road safety of someone who is drunk who is driving. He will injure himself, and even he's a threat on the other drivers. So that's why we should be able to detect the site on time. So it means that to be able to detect, we cannot rely anymore on this field sobriety test. So that's why we would like to be able to, what are the other means, verification means of a guy who is, for example, be able to drowsy. This drowsiness detection, it's useful for this Bolt, for all its mobility as a service, but also for all the logistics company where we have trucks driving. So this detection should be done on the edge in order to protect the GDPR, the privacy, and to ensure the timely decision making. This guy, it means that we should be able, as soon as we detect that this guy is drunk or not in condition to drive, the engine should be cut. So that's why we should be able to develop this on the edge models. So let us back quickly to, sorry. Yes. So this, the Vision Zero, which is by 2050, the plan is to end traffic-related fatalities and serious injuries by taking systematic approach to road safety. So, and then all these KPIs about speeding, seatbelt and child restraint system, helmet, alcohol, distraction using the handheld mobile device. So it means that for us, the distraction, the KPI distraction, is only using a handheld mobile device, yes or no, which is no. What is the vehicle safety? What is the PI infrastructure? For example, what is the impact of the speed, the overspeed? You know, the direct cause of 30% of all the fatalities. It means that if we better detect the speed, so the huge potential of car accidents. So the idea to, I was discussing with Amir this morning. So this is the low latency architecture that we are suggesting and we are thinking about it. In this, there are 3 layers: the edge layer, the fog layer, and the cloud layer. So the idea, we have cars. But, you know, on the road, we do not have only cars. So this is why is the first weakness of my architecture is this one. On the road, there is not only. You have what we call this VRU, which stands for Vulnerable Road Users. We have scooters, we have bicycles, we have pedestrians, and we have drones. And 2 days ago, a drone was bringing drugs from Jordan to Syria. So it means that next time, drones will be able to bring anything, and they are kind of part of the ecosystem. Part of the ecosystem, since it means that we need to take them in consideration and to consider the threats and the caveats for using the drones. These cars, suppose that we have vehicles, and these vehicles are able to communicate with each other. Okay? So what is this communication, for example? This communication, there is this V2V, vehicle to vehicle, and also we have this V2 infrastructure. What I mean by infrastructure can be, for example, this traffic light, or what we call this roadside unit. So the vehicle, they are able to manage this roadside units. We have a kind of community. Any question? What is the caveat? The problem that if we have cars, they are communicating with each other, we're exchanging, we're enriching each other, there's a risk. Whenever there's communication, there is a risk of intrusion detection. First question, first threat, how can I detect promptly, on time, this malicious card? First. Good. I would like to be able, let's keep in mind that we are in Berlin, we are Paris, thousands of cars. We are in Place de la Champs-Élysées in Paris, thousands of cars. It means that we need to limit the communication between cars and the roadside units, the fog. Then who will be on charge to ensure the communication? So that's why the task, who will be what we call this cluster head? And, to avoid what we call this single point failure, we need to have this cluster head backup. So one of the things that we need to, to limit the communication with the roadside units is to elect what we call this cluster head. Then how to choose the cluster head? But you need to keep in mind this low latency requirement. Cars are moving. Cars are moving. It means I'm the cluster head. In a blink of an eye, I'm not anymore the cluster head, and the framework needs to elect a new one. So that's why we need to have the most reliable cluster head, but promptly. We need to be careful that the cluster head is the entity, the vehicle, who is responsible for ensuring the communication with the roadside ones. It means this entity should not be malicious. Why? Suppose that, Amnir, when you are leaving your place in the morning, you are normal. As soon as approach to Delta ESSCaSS, your car becomes mad and you start to behave as a malicious car. So it means this is the rules of the game. It means that you can change your status at any time. And the concept, you need to be detected and to be kind of blacklisted as soon as possible. The challenge is very important, since if you become cluster head and malicious entity, you are eager to transmit to the roadside units false information, and then you are faking the game. It means that you start, transmitting information on behalf of 100 vehicles. It means that you are telling to the roadside units that we are huge congestion in front. This is nice blind. He's only trusting the cluster head in terms of exchanging the information. Then we need to be able to say that this vehicle is not trustworthy anymore and needs to be, blacklisted. So this is the challenge. For example, in case of crisis, and we can see that the cluster head, the roadside tuners is not able to work properly, then we need to provide kind of ad hoc roadside tuners. This can be done by drones. Then we enter in the scope of management, fleet management of drones, to ensure the road security role. So this is, the challenge that we have already in the field, in the ground. Okay. And as I will show you, we started developing some approaches, and I would like to take your opinion. What do you think about that? What I will tell you, who is electing the cluster head? Is this roadside units? This, I'm coming. Hello, I'm here. I'm in your range. It means that we can only elect the cluster only within the range of the roadside tunes, which is around 300 meters. Or I would say, we are strong enough as vehicles, and we can organize ourselves in terms of communities, and we can elect our cluster head among us. There is no need to involve the cluster head and to provide the new bundle. So this is what we developed now. It is the new, the second pathway in terms that we have not to involve the pathway in our things. Okay? The roadside tunes in our things. So this is what we have done for the edge layer, the ground layer. Now, then we come into play this nice fog. Actually, the goal is we are collecting information that we need to, the goal is not only collecting information, we need to bring them to have these insights. So the god of the knowledge is this SDN controller, this cloud layer. But this cloud layer actually is too far. So that's why we need to have someone in the closer to, or in the between the edge and the cloud. So that's why we have this fog. So this fog layer, which I would say it is the set of roadside, the community of roadside tunes or traffic lights. We have the other second challenge. The second challenge is how to secure the fog layer. And we have also, which is out of the scope of this talk, how to secure the cloud layer. What we are suggesting is since it's still manageable, is to use the blockchain technology, distributed ledger technology, blockchain, to secure the fog layer. Okay? And what we will see that the cloud, so the cloud layer, the SDN control will you have two types of services. The first service to this network services. For example, I will explain this task scheduler in terms of offloading. It means that we need to keep in mind that the fog have no computation power as the cloud. It means that when he's resourceless or is out of resources, he will ask help. So that we call this offloading. Then the cloud has to provide the right source. And since there's not only one fog node is asking, then we have to use this, what we use this reinforcement learning to find the right fog node to assign the right task. This is one. So there is management, I will call this network services that provide by the cloud layer. In addition to that, the cloud layer is responsible of processing data. But there is two types of data. And it depends on the decision making. For example, since you are collecting data from the edge layer, there is this, I would say, real-time need. Real-time need, for example, can be the traffic light management. So this is why the traffic light management is one of the services of the new framework, the new architecture. The second one is the change dynamically of the speed limit. So it means that we need to keep in mind that from now on, these 50 signals, they will change dynamically depending on the states of the congestion. And this one road status or two road, for example, states can be changed to one road in order to manage better the congestion. Do you know that why it would be interesting to adapt the speed limit? As one complementary action to the traffic light, if you change the speed limit, if you lower the speed limit, it means that you are lowering the number of cars arriving to the traffic light. Then you are better managing the congestion. So this is what I call the services. The other types of services that will be developed by the cloud layer is this I would call them dedicated services. For example, the collision detection, the road safety management, the trajectoriness, all the strategic decisions that can also be detected. For example, do you have any idea how the speed, the KPI speed will be fulfilled? It will be by these things. Do you know from now on, as you are contributing, each vehicle will contribute to the control of the speed of the other vehicles. It can be, I was discussing with Amir this morning, it can be a vehicle, it can be a scooter, it can be a bicycle who is, exchanging high definition video. And this high video that can be processed by the cloud layer to detect the overspeed. That means that you will have received of overspeeding fine at your place thanks to the contribution of all the citizens. So that's why if you know that the speed is responsible of 30% of the casualties, that you feel that doing so, we will have a better verification computation of the KPI of the speed, and we will lower all this overspeeding. Still I have time? Yeah.
10 minutes.
And I have plenty of slides too. So now, the idea that I would like that we discuss together in detail. Okay? I'm lost. So what we have done simulation. Yes, it's here. So we have used Sumo, and then this simulation for urban mobility, and as you will see, Sumo is not the best of the simulator, okay? And especially when try to simulate this V2V, vehicle-to-vehicle simulation. So for the vehicles, we were computing the ID, the lane ID, acceleration, the speed, type, bus, car, ambulance, and further in the length, the waiting time of vehicles in the lane. So let's see how we are doing the cluster head. So the cluster head, with the idea that we are strong enough, we are smart enough, so since we are organizing the cars in communities, then each car is computing a score, this EMB, and this EMB and the car in this lapse of time, the highest one will be the cluster head, and he will be selected among the community to be in charge of communicating with the roadside twins. So that's why the car, so the company of this rank, we call this EBM, egocentric betweenness metric. So the car with the best ranking is the cluster head, and the second one will be the cluster head backup, and other ones will be the cluster members. So this is what we have done. So here we have 3 clusters, and we were able to compute for each car will compute its own score. How it works? For example, this ones, we have the cluster 1 here. As I told you, each vehicle will be able to compute its score. Okay? And then, for example, this one in the cluster 3, 593 will be the cluster head. Okay? So how you compute this score? This I'm showing a little example. For example, the car 1 here is able to compute this score as EBM over which is 0.5. So this is the formula for computing the cluster head for this car. Okay, so this is what. Yes.
Sorry. So you're explaining the algorithm. I'm wondering what is kind of the optimization objective? Have you also tried to formalize that? Like what is a good clustering? What is the good way of assigning the cluster heads?
The cluster head here, it's this is one of the that we find in the literature, but there is other approaches too. So for me, I was able to hear this my situation, for example, and I would like to be able as vehicle to compute this egocentric betweenness. It means that, if I am able to touch my neighborhood, so the idea I'm able to this betweenness, I'm able to touch down all of the ones of the neighborhood. I should be the cluster head, since I'm able to transmit information of the maximum number of cars.
Almost could be the objective then, to kind of make sure that each of the cars can kind of get communicating with the maximum number eventually.
Yes.
Yeah.
The other approach that is about radio strength. The other one I would say speed. you cannot be the cluster head since you are over speeding. Do you know why? We want to maintain your status as a cluster head, the maximum length of time, the longest time, period of time, since we do not have to restart computing. Yes, Samir.
Sorry again to jump in. So I will just complement what Melis was asking. So if I understood correctly, your answer to Melis was, so the approach is to select the car that has the highest number of visibility with
Yes.
with the peers. Okay. So how, and since you mentioned the speed, as we know, like when it comes to either network or vehicle-to-vehicle communication, V2V, or even V2I, one of the issues is speed. The moment we have some threshold over there, then we start having either data corruption or signal loss and so on. Is this something that is addressed also in your?
Not yet.
Not
No.
yet. Okay.
So this is, I'm grateful to the French internship that we had this summer in Tartu. He is a strong guy, so he teaches me a lot. So we are exploring all of this together. So all this one, all these results, all this slide, they are its own work. So, and then we are just exploring. This is what was done by him. He told me that let's keep the roadside tunes out of this cluster selection. And then, so, then we have the first initialization and of how we can start by selecting the cluster head, and then how we can maintain the cluster head and the cluster head backup. So this is the outcome of our simulation. So the red ones, they are the cluster head. So here we are able to whenever we are on the road, you are able to have the cluster head, which is unfortunately not be the case if you are rely on the roadside tunes to compute the cluster head, since you will be only when you should be in the range of the roadside tunes. So the green is the cluster head backup, and the blue the cluster member. So what I want to show is that's doable. He wants to show that we are really scalable with 1,200 vehicles. Yes, thank you. You are saving my life. So here it's what I want with is the number of the cluster head. And he showed that the more we're increasing the number of cars, the number of cluster head is decreasing, since we're building the cluster really, and then we have members works on the cluster. So I need to really speed up. So what we would like to do is to use the Omnet++ to have to be able to take consideration this V2V. The prediction of the arrival vehicle. This is a very important thing. If you would like to have the low latency, you need to also to predict to which direction the car is heading to. So it means that you need to be able to predict, take this car, what would be the next RSU, to let this RSU know and to anticipate. It means that the next RSU will run the cluster head, if any, if you are letting know the next RSU that this car or this vehicle is coming soon. Then he will also apply the traffic light control. We are using this, so currently we didn't apply the Kalman filter, okay? So, and we need to improve it by using the Kalman filter to compare the precision. So, what we plan for the future is to use our friend of trustworthiness left today. So, it's to say that the RSU has now we have to give the role to the RSU, this other approach, the other pathway, to say, Amnir, you are a cluster head if you are computing to have the best of the trust score, which is, we need to compute the behavior score, the reliability score, and the traffic rules. To compute the behavior score, we need to have speed, acceleration, lane change, the reliability score, the past performance, communication reliability, traffic rule score, the compliance. And then we are started thinking how we can use this trustworthy vehicles. So trustworthy vehicles, we need to take into consideration your what you have already done during the next RSU, the previous RSUs, in order to take consideration you are really, I would say, a good driver or trustworthy driver, and you are. So I have so many things to say. So, so this is, we would like to predict the trust score and the anomaly detection. So the anomaly detection, I need 2 minutes. So here we have to take consideration what we are already work on is to, for the intrusion detection, we need to keep in mind this, if you are able to, this what we call this post-deployment AI. What you need to keep in mind that if you build a model on data, and in the meantime data change, for example, for the month of June, there's a lot of detection of anomalies in Tartu, but in July, it's not the case. It means that we need to keep in mind that the concept of data drift, this post-deployment aspect, it means that if you build a model, this model will provide high performances as soon as there is no data drift. So that's why we need to keep in mind that to maintain this something that can be detected by the cloud layer. The cloud layer has to ensure that there is no data drift, otherwise he has to retrain in incremental manner the model for example, intrusion detection. Sorry, I have so many things to say, but so thank you very much.
Don't worry, we will have the boat trips, people can approach you, you can still say many things in private.
Okay.
Today and tomorrow. Do we in the auditorium have any question? He had many things to say. No? I can see that people are
Shy.
Oh, there was. Okay, Amnir. Next.
It's me. So I have one small question actually. So you, on one of the slides, you showed that 30% of the accidents are caused by high overspeeding, basically. So it's just, I just want to know if you have any intuition why the overspeeding warnings have not been implemented in the vehicles that we have today. You know, like maybe just when you don't wear a seatbelt, you have this beep. Why not a beep?
There is no verification means. Now, from now on, we would like to vehicles should be able to exchange this high definition video. It means that if Yak is overspeeding, it is, we have the evidence that when he will be fined. So the idea is how to take this video and how to, leave it to the safe space where it can be processed.
But you know the Estonian debate at the moment that these average speed cameras are being discussed. Now there are these automatic cameras, but there will be average speed cameras potentially on the roads. All of this has lowered the speeding as well. But thank you. Again, please, applause.
Thank you.